Good morning, everyone. Welcome back. Today we're embarking on a brand new and incredibly important chapter in our physics journey. As you can see on the screen, this is Chapter 4, Part 1, and our focus for the next few sessions will be thermal physics. This area of physics is all about understanding heat, temperature, and how energy moves and transforms within systems, from the microscopic interactions of atoms to large-scale phenomena. We'll be exploring key concepts like specific heat, latent heat, and the laws of thermodynamics. As a proud part of Misr University for Science and Technology, represented by our emblem at the top, Dr. Mohamed Ali, am eager to guide you through these fundamental principles. Let's dive right in. When an object is heated, it gains thermal energy. This increases the kinetic energy of its molecules, and therefore its internal energy. Temperature, then, is a measure of an object's degree of hotness or coldness, essentially reflecting its internal energy. Heat, on the other hand, is the energy times transferred times between objects specifically due to a temperature difference. Looking at our diagram, you see hot object A and cold object B. The arrow clearly shows heat flowing from A to B. This process leads us to times thermal equilibrium times. When objects A and B are in contact, heat exchanges until their temperatures become equal. At this point, the net heat transfer ceases, and they are in thermal equilibrium. Alright everyone, let's delve into thermodynamics. This field, as you might recall, is essentially the area of physics studying the transfer of heat, crucial for understanding how energy moves and changes forms. Today, we're starting with a foundational concept, the Zeroth Law of Thermodynamics. This law states that if object A is in thermal equilibrium with object B, meaning no heat flows between them, and object C is also in thermal equilibrium with object B, then it follows that objects A and C will inherently be in thermal equilibrium if they are brought into direct contact. Look at the diagram on the right. In the top part, we see A and B. If there's no heat flow, they're in equilibrium. Then, in the middle diagram, B is in equilibrium with C. What the Zeroth law concludes, as shown in the bottom diagram, is that A and C must also be in equilibrium, meaning no heat will flow if they times are brought together. It's a fundamental principle for defining temperature. Absolute zero, defined as 0 Kelvin or negative 273.15 degrees Celsius, is the lowest possible temperature an object can ever reach. We commonly use three temperature scales, Celsius, Fahrenheit, and Kelvin. For water, the freezing and boiling points are 0 degrees Celsius and 100 degrees Celsius, 32 degrees Fahrenheit and 212 degrees Fahrenheit, and 273 K and 373 K, respectively. Notice figure 4-4 on the right, which provides a clear visual comparison of these three scales and their key reference points, including absolute zero. You'll also find the conversion formulas, like Tk equals Tc plus 273.15, provided on the slide for quick reference between them. Alright class, let's look at example 4-1 on temperature conversions. For part A, we're asked to convert 75 degrees Fahrenheit to Celsius. We use the formula Tc equals 5 divided by 9 times, Tf minus 32. Substituting 75 for Tf, we get Tc equals 5 divided by 9 times, 75 minus 32, which simplifies to 24 degrees Celsius. So, a pleasant 75 degrees Fahrenheit is equivalent to 24 degrees Celsius. Now for part B, we need to convert minus 2.0 degrees Celsius to Fahrenheit. The conversion formula here is Tf equals 9 divided by 5 times Tc plus 32. Plugging in minus 2.0 for Tc, we have Tf equals 9 divided by 5 times, minus 2.0, plus 32. This calculation yields 28 degrees Fahrenheit. Quite chilly, indeed. Let's tackle a classic problem. What temperature is numerically identical on both the Celsius and Fahrenheit scales? To find this, we set the Fahrenheit temperature, Tf, equal to the Celsius temperature, Tc, and call it T. So, as shown in step 1, we use our conversion formula and have T equals 9T divided by 5 plus 32. Following step 2, we move all terms involving T to the left side. This gives us 1 minus 9 divided by 5, T equals 32, which simplifies to -4T divided by 5 equals 32. Solving for T in step 3, we find T equals -40. And as a check in step 4, substituting -40 degrees Fahrenheit into the Celsius conversion formula, Tc equals 5 divided by 9, Tf minus 32, gives us 5 divided by 9, minus 40 minus 32, which perfectly equals -40 degrees Celsius. This confirms our insight, -40 degrees is the unique point where the two scales align. Now, for your practice, try the your turn problem below. Experiments have shown conclusively that there is a lowest possible temperature, below which it is impossible to cool an object. This is referred to as times absolute zero times. To understand this, consider the constant volume gas thermometer shown in the top right figure. We cool or heat a gas, carefully keeping its volume constant by adjusting the mercury level, H. We then calculate the gas pressure using the formula P gas equals P at plus rho GH. When we plot the gas pressure, P, against its temperature, T, for various gases, we obtain these straight lines, as shown in the bottom figure. Notice how each gas yields a different line, but when we extrapolate these lines backwards, they all converge precisely at a single temperature where the pressure would theoretically become 0, minus 273.15 degrees Celsius. This universal point is our absolute zero. Alright, let's tackle example 4-2. We have a gas in a constant volume thermometer. We're told that at 0 degrees Celsius, its pressure is 80.0 kilopascals. Assuming ideal behavior, as shown in the graph, we need to find the pressure of this gas at 105 degrees Celsius. Notice the graph plots pressure P against temperature Tc. This linear relationship can be expressed as P equals m plus c, where m is the slope and c is the y-intercept. We know one point, at T equals 0 degrees Celsius, P equals 80 kilopascals. We also know that for an ideal gas, pressure approaches 0 at absolute zero, which is minus 273.15 degrees Celsius. So, we can calculate the slope m as the change in pressure divided by the change in temperature, m equals 80 minus 0, kPa divided by 0 minus 273.15 degrees C. This gives us a slope of 0.293 kilopascals per degree Celsius. The y-intercept, C, is simply the pressure at 0 degrees Celsius, which is 80 kilopascals. Our equation then becomes P equals 0.293 kilopascals divided by C degree, times T plus 80 kilopascals. To find the pressure at 105 degrees Celsius, we substitute T equals 105 degrees Celsius into this equation. Calculating this gives us P equals 0.293 times 105, plus 80, which equals 111 kilopascals. Alright, let's look at exercise 4-1, converting 55 degrees Fahrenheit to the Kelvin temperature scale. This involves a two-step process. First, we convert from Fahrenheit to Celsius. As you see on the slide, the formula is Tc equals 5 divided by 9 times Tf minus 32. Substituting 55 for Tf, we calculate Tc equals 5 divided by 9 times 55 minus 32, which simplifies to 5 divided by 9 times 23, giving us 13 degrees Celsius. Now, for the second step, converting from Celsius to Kelvin. This is simpler, T equals Tc plus 273.15. So, we add our 13 degrees Celsius to 273.15, resulting in 286 Kelvin. This final value of 286 K represents the temperature on the absolute Kelvin scale. Alright, let's dive into thermal expansion, starting with linear expansion. As you see in the diagram on the left, an object with an initial length L0, when subjected to a change in temperature, delta T, will experience a change in its length, delta L. This change in length, delta L, is directly proportional to both its original length and the temperature difference. We define this relationship mathematically as delta L equals alpha times L0 times delta T. Here, alpha is known as the coefficient of linear expansion. It's a material-specific property, indicating how much a material expands per unit length per degree of temperature change. Its SI unit is inverse Kelvin, K superscript 1, which is equivalent to inverse degrees Celsius, C degree, superscript 1. Notice the table on the right. It provides various coefficients of linear expansion for common substances, showing that materials like lead expand more than, say, quartz, for the same temperature change. Alright, let's look at this conceptual checkpoint comparing thermal expansions. We have two rods. For rod 1, with an initial length L0, when it's heated by an amount delta T, its length increases by delta L, as shown in the diagram. Now, consider rod 2. It's made of the same material times as rod 1, meaning its coefficient of linear expansion, alpha, is identical. However, rod 2 is twice as long as rod 1, so its initial length is 2L0. If rod 2 is heated by the same amount times, delta T, what will be its increase in length? Will it be delta L, 2 delta L, or delta L divided by 2? Recall the formula for linear thermal expansion. Delta L equals alpha times L0 times delta T. Since alpha and delta T are the same for both rods, the change in length, delta L, is directly proportional to the initial length, L0. Therefore, if rod 2's initial length is twice that of rod 1, its expansion will also be twice as much. The answer is, B, 2 delta L. Let's consider an interesting application of thermal expansion with the iconic Eiffel Tower. It stands 301 meters tall on a 22 degrees Celsius day. Our question is, how much does its height decrease when the temperature drops to 0 degrees Celsius? We use the formula for linear thermal expansion, delta L equals alpha times L0 times delta T. From the problem, L0 is 301 meters. The change in temperature, delta T, is 0 minus 22 degrees Celsius, giving us minus 22 Kelvin. The coefficient of linear expansion for iron, alpha, is 12 times 10 to the power of minus 6 per Kelvin. Plugging these values in, as you see on the slide, delta L equals 12 times 10 to the power of minus 6 K inverse, times 301 meters, times minus 22 K. This results in approximately minus 7.9 centimeters. So, the Eiffel Tower contracts by about 7.9 centimeters when it cools down. A clear demonstration of how materials respond to temperature changes. Let's explore some crucial applications of thermal expansion. First, consider the bimetallic strip, like the one shown in diagram D, for a thermostat. It consists of two different metals, A and B, bonded together. Metal B has a greater coefficient of expansion. So, when heated, B expands more than A, causing the strip to bend. This bending action connects or breaks an electrical circuit, precisely controlling heating or cooling systems. Next, we have anti-scalding devices in water taps, illustrated in the middle diagram. If the water becomes too hot, a thermally sensitive component within the device expands, moving a plunger. This movement reduces or even stops the flow of hot water, preventing accidental burns. Finally, expansion joints are vital in large structures. Observe the bottom images, in bridges, railroad tracks, and oil pipelines. Materials expand when hot and contract when cold. Without these deliberately designed gaps or curves, like the zigzag joint in the road or the large loops in the pipeline, structures would buckle, warp, and sustain severe damage from temperature fluctuations. Here's a diagram of a bimetallic strip thermostat. The dial, labeled 1, is set to 10 degrees. Connection 2 leads to the bimetallic strip, marked 3 and 4, which is crucial because it bends with temperature changes due to its different metal layers. Notice its current position, it's clearly curved outwards, creating a gap from contact point 5. This open circuit means the system is currently in the off state, as indicated. For the system to turn on, the ambient temperature must drop below 10 degrees, causing the strip to cool, bend inwards, and make contact with point 5. If an object's length changes with temperature, then logically, its area must change as well. Let's consider a simple case, a square piece of metal with initial side length L. Its initial area, A, is simply L squared. Now, if we increase the temperature by delta T, each side length expands. Remember, the change in length, delta L, is given by alpha L delta T. So, the new side length becomes L plus alpha L delta T. The new area, A prime, will be this new side length squared, L plus alpha L delta T, squared. Expanding this, we get L squared plus 2 alpha L squared delta T, plus alpha squared L squared delta T squared. Here's an important simplification: since alpha, the coefficient of linear expansion, is very small, alpha squared will be extremely tiny, so we can neglect that last term. This leaves us with a prime approximately equal to L squared plus 2 alpha L squared delta T. Since L squared is our initial area A, we can write a prime as A plus 2 alpha A delta T. Therefore, the change in area, delta A, which is A prime minus A, simplifies to approximately 2 alpha A delta T. This shows how area expansion relates directly to linear expansion. Here's a common conceptual question about thermal expansion. If we have a washer with a hole in the middle, and we heat the entire washer, what happens to that hole? Does it expand, shrink, or stay the same? Let's look at the diagram. Imagine this washer. You can think of it as if it were a solid disk with a smaller inner disk removed. When we heat a material, it expands. Crucially, it expands uniformly, as if you're placing the object under a magnifying glass. Every dimension gets larger. This means the outer diameter expands, and importantly, the inner diameter, the hole, also expands. Notice in the lower diagram, after heating, both the washer and the removed inner disk have grown. So, the answer is, the hole expands. When a solid is heated, its volume expands. This principle also applies to holes within a material. The volume of a hole expands as if it were filled with the same substance. Notice the diagram on the right. Heating a container causes its internal volume to expand, much like the original block would. For a quantitative understanding, if we consider a cube with initial volume V equals L cubed, an increase in temperature, delta T, leads to a new volume V prime. After expanding, L plus delta L, cubed and simplifying by neglecting very small terms, we find the change in volume, delta V, is approximately 3 alpha V delta T. This leads us to the general formula for volume expansion, delta V equals beta V delta T. Importantly, beta, the coefficient of volume expansion, is exactly 3 times the linear expansion coefficient, alpha. Alright, let's tackle example 4-3, oil spill. We're considering a 150 cubic centimeter copper flask, full of olive oil, heated from 6.0 to 31 degrees Celsius. We need to find the volume of oil that spills. Look at the diagram. Heating causes the oil to overflow. This happens because the olive oil expands more significantly than the copper flask for the same temperature increase. First, we calculate the volumetric expansion of the olive oil using its coefficient beta. That's delta V equals beta V delta T, giving us 2.6 cubic centimeters. Then, we calculate the flask's expansion. For a solid, we use 3 times its linear expansion coefficient, alpha. So, delta V for the flask is 3 alpha V delta T, which comes out to 0.19 cubic centimeters. The spilled volume is the difference, 2.6 cubic centimeters minus 0.19 cubic centimeters, resulting in 2.4 cubic centimeters of oil spilling out. A clear case of differential thermal expansion. Alright, let's explore a fascinating characteristic, the special thermal properties of water. Look at the graph on the bottom left. It shows how the density of water, defined as mass m divided by volume V, changes with temperature. What's truly unique is that water reaches its maximum times density at about 4 degrees Celsius. If you follow the magnified section on the top right, you clearly see this peak. This means when we cool water from 4 degrees Celsius down to 0 degrees Celsius, it actually becomes less times dense and expands. This counterintuitive behavior is crucial, influencing everything from ice floating to aquatic life surviving winter. This slide clearly demonstrates a very practical consequence of water's anomalous expansion. Looking at the image, you see a burst water pipe, actively leaking, surrounded by the ice that caused the damage. When temperatures drop below freezing, water inside these pipes solidifies into ice. But unlike most substances, water expands significantly when it freezes. This expansion exerts enormous outward pressure on the pipe walls. The pipe simply cannot withstand this internal force, leading to a rupture and costly damage. It's a prime example of water's unique volumetric change upon freezing. When winter temperatures drop in northern latitudes, the surface waters of a lake begin to cool. Crucially, as water cools to 4 degrees Celsius, it becomes maximally dense. This denser water then sinks, allowing the warmer water from below to rise and be cooled in turn. This cycle continues until the entire lake reaches a uniform temperature of 4 degrees Celsius. However, further drops in temperature, times below 4 degrees Celsius, cause water to become less times dense. So, the cooler, less dense water stays at the surface, where it then freezes. This forms a protective layer of ice and snow on top, which acts as a vital thermal insulation, slowing the continued growth of ice downwards. Think about what would happen if water exhibited ordinary behavior, like most liquids, shrinking when cooled, with its solid form being denser. Ice would then sink to the bottom, and lakes would freeze from the bottom up. This would quickly freeze the entire lake solid, a truly disastrous outcome for fish and all other aquatic creatures. We're looking at the crucial role of thermal expansion in dentistry, a fundamental physics concept with significant practical implications. First, for a dental filling, the coefficient of thermal expansion, alpha, of the filling material must closely match that of the natural tooth enamel. Notice the top diagram. If the filling's alpha is greater than enamel's, a significant gap forms when cooled, for instance, by a cold drink. This leads to what we call marginal percolation, allowing liquids and bacteria to seep in, causing further issues. Likewise, denture-based materials alpha needs to match the synthetic teeth, ensuring they expand and contract together with hot or cold food, which is essential for stability. You can see an example of a denture in the middle image. Finally, dental waxes, crucial for creating patterns for restorations, have a large times alpha. Their significant contraction upon cooling requires careful compensation during the fabrication process to achieve accurate final restorations, as exemplified by the wax tooth models shown at the bottom. As we conclude our session on physics topic, e.g., the principles of energy and motion, today, I want to extend my sincere thanks. This beautiful image, likely our campus at sunset, is a perfect reminder of physics all around us, from the scattering of light painting the sky, creating these vibrant hues, to the structural design of the buildings we observe. Your engagement and thoughtful questions throughout our discussion have been truly invaluable, making our exploration of these fundamental concepts incredibly rewarding. Thank you for your active participation. For more information about our university and programs, please visit www.mus.edu.eg.